We're going to look at another slightly different test now, and this test is called the chi-squared test of independence. So that funny X thing is actually a Greek letter chi. In this test, we are asking whether two nominal or ordinal variables are independent of each other. An optometrist has recorded the following data. So of all their patients, the optometrist has recorded whether they had blue, green or brown eyes, or whether they wore glasses or didn't wear glasses. And we'd like to know whether wearing glasses and eye colour are independent of each other. So our null hypothesis is that eyesight and eye colour are independent of each other. That's the most precise thing you can be. And our alternative hypothesis is the opposite of that, is that the eyesight and eye colour are not independent of each other. So think back to probability now. What did two variables being independent mean? It meant that the probability of them happening at the same time, so the intersection of variable A and variable B, was equal to the product of the probability of A and the probability of B. So if they were independent of each other, them happening at the same time, you could multiply their probabilities. And we are going to use that fact here to start thinking about whether eyesight and eye colour were independent or not. So what are the probabilities of our variables? So what is the probability of wearing glasses? Well, our best guess for that, even though this is only a sample, our best guess for that is the number of people wearing glasses divided by the number of people who are there. So that is 165 plus 253 plus 176 divided by how many are there altogether. And if you count all those up, there are 1,673 patients here. And we get a probability of wearing glasses is 0.355. We can do the same thing for people who are not wearing glasses. That's 0.645. And then we can do the same thing for each of the eye colours. How many people with blue eyes have we got divided by how many people are there? How many people with green eyes and how many people with brown eyes? I've written these at the ends of their respective rows and columns. So you should see that adding up these two should equal 1 and adding up these three should equal 1. Now, if these two things are independent, what is the probability that we choose a blue-eyed person who wears glasses? So if these two things are independent, that should be the probability of wearing glasses, 0.355, multiplied by the probability of having blue eyes, 0.312. And then we want to see how different is that to what we actually got, which is 165 over 1,673. An equivalent way of saying that is, if these two things are independent, how many people would we expect to have both blue eyes and glasses? Well, let's work that out. First of all, what is the probability of wearing glasses and having blue eyes at the same time? Now, if these are independent, that would be the probability of wearing glasses multiplied by the probability of having blue eyes. Now, from our table, we worked those out to be 0.355 multiplied by 0.312. That gives 0.11076. We had a sample size of 1,673. Now, each of those 1,673 people in our sample could be considered a random trial, where they can either have glasses and blue eyes or not. The law of large numbers then tells us the more trials we do, and we've got quite a lot of trials here, we would expect the proportion of people with glasses and blue eyes to approach the probability of having glasses and blue eyes as this gets bigger, and this is fairly big. So how many people would we expect to have glasses and blue eyes? It would be this proportion of this. we would expect there to be 1673 multiplied by 0.11076. So we would expect there to be, that comes out about 185.3 something. Okay, so we would expect the number of people with both blue eyes and glasses to be 185.33. And I've just done that with every possible cell. So we'd expect that many people, and we received that many people. Like, if that's a big difference between those things, then surely this assumption that we can multiply the probabilities must be wrong. So if there's a big gap between the expected and the observed, we can probably say our null hypothesis is wrong. Whereas if there's not much of a big gap between the expected and the observed, we can't say it is wrong. We don't have enough evidence. Starting to sound like a statistical test now. So what we are going to do, we are going to come up with some sort of measure of how different those are. And that measure we are going to use is called the chi-squared statistic. Take the difference between OI, which is what we observed, minus EI, which is the expected. So what we observed minus the expected, so that's the distance between them. Square it, because we don't care if it was smaller or bigger. We just care that there was different. Normalize it so that we scale it down so that everything's on the same scale. So we divide by how many we expect. So the observed minus the expected, which is the distance, square it, don't care about the distance, divide by the expected so that we scaled it down so we're comparing everything together, and then sum all those up for every cell in that table. For example, in this case, we would have the first cell, 165, minus what we expected, 185.33, square that, divided by 185.33. So that was blue eyes and glasses. The next cell, which was green eyes and glasses, so we'd add to that 253 minus 231.85 squared, all over 231.85. And we do that for every cell in our table. And we get this chi-squared value of 6.4544. Okay, that's not comparable yet to anything. What would we expect that to be? So if our null hypothesis was true, if these were independent, then the observed and the expected would be very, very close. You'd hope they'd be the same. So if they were the same, we'd be adding up a lot of zeros. Or if they were really, really close, we'd be adding up a lot of small things. So we'd expect that to be really small. And if these were really, really far away, we'd expect that to be a big thing. Statisticians before us have looked at this particular statistic and can say that this statistic will follow a certain distribution, and we can work out p-values from that. What's something else that will affect the size of this? Well, it's how many things you are summing up, right? If we're very, very close, but we've got 100 cells, you're going to be adding a lot of things because all these are positive. So the distribution of this chi-squared value is going to depend on how many cells we've got. And that's going to depend on the shape of that table. One way of measuring the shape of this is we're going to start calling something called the degrees of freedom. So if we let C be the number of columns, which is 3, and R be the number of rows, which is 2, then our degrees of freedom, nu, this funny V, is going to be C minus 1 times R minus 1. So in this case, our degrees of freedom is going to be 2 times 1, which is 2. We have 2 degrees of freedom here. And just think of that as a measure of how many things we're adding up together. Now, I said statisticians before us have come up and managed to work out the probabilities associated with chi-square values. And what we are going to do, we're going to compare that, like we did with the normal tables, we're going to compare that to chi-squared tables. This is chi-squared tables that are in your notes. And what this looks for is a critical value of chi-squared. So given what the columns here are the confidence levels, and we said 95%. And what our degrees of freedom, that's the rows, and we had 2. So we've got 2 degrees of freedom and 95% confidence. Then our critical value of the chi-squared statistic is 5.991. What does that mean? It means that if our chi-squared value is bigger than this critical value, then the difference between the observed and the expected is too big, therefore the null hypothesis must be wrong. But if it's smaller than that, we say actually it's not big enough to say it's wrong. So we are always going to be comparing our chi-statistic to something in this table, and we find that by going over to our confidence level and down to our degrees of freedom. In this case, we compare it to 5.991. So our chi-squared statistic was 6.4544. Our critical value of the chi-squared statistic that we're comparing to is 5.991. As our chi-squared statistic is bigger than the critical, we are too far away from what we expect, and so we can reject the null hypothesis and say what we expect is not really what we expect. Our null hypothesis must be wrong. Just like any other hypothesis test, there are some assumptions that this uses, and we can use these as checks to go, can we use the chi-squared test of independence or not? So what are they? That we are dealing with nominal or ordinal data. Okay, we are not dealing with interval ratio data, nothing continuous. That the things inside our cells are frequencies. What does that mean? That means counts. So we haven't got sort of mean values of anything in there. Like the thing in our cells is just how many things there are. All our categories are mutually exclusive. So one of the assumptions is that you can either wear glasses or not. You can't be both. You can either have blue eyes or green eyes. You can't be both. And an important one is that each cell of the table contains at least 5 observations. So in our table, each cell must have a number bigger than 5.